Today we're going to talk about steganography. Now, according to the FBI, this picture that I have on my desktop, this picture has the map of an airport hidden within its data. So it looks like a pretty normal picture, right? Now, this picture, it contains data, and it hides this data within the pixels of this image. Okay, and if you continue reading the article, it says that the exact details. So although the exact details of what the supposed Russian agents embedded in the pictures and how they did it remains classified, the basic technique involves changing the numeric code that computers assign to colors. And to generate the picture of the computer screen, the computer assigns every pixel 3 numeric values. That's the RGB. So you have the red, the green, the blue, and the color. They give the pixel the right color, right? And that's 1 pixel. By changing those values ever so slightly, the spies could hide the ones and zeros of computer language in the picture's pixel numbers, and those 1 and zeros, those are binaries, and you can convert them to plain string. And I'll show you how to do that in Python later, right? But without altering the picture's appearance to the human eye. So most of the time you can't tell. If I show you a picture that has been altered and a picture that have not been altered, you can't tell. And we're gonna go through some of these exercises later. You're gonna see it anyway. But let's talk a little bit about this this is actually called steganography. And steganography is the process of hiding information into an object such that the naked eyes can neither recognize its existence nor extrapolate any meaning from it, because you can't even see it in the first place, right? So to an ordinary person, an image with a hidden embedded image, when executed well, would seem perfectly identical to the original image. This has actually been this has a rich history actually. So the first recorded use of steganography can be traced back to 440 BC in Greece. So there is this royalty, I think a king, sent a message to his vassal called Aristogoras by shaving the head of his most trusted servant. Some version of the history will say that he's a slave. So he shaved the head of the slave and then marking the message onto his scalp on the head, right? So pretty much writing the message onto the scalp and then sending him on his way once the hair has regrown. So with the instruction, so the message says this, right? It says, when thou art come to Miletus, bid Aristogoras shave thy head and look thereon. So pretty much when the slave has arrived to the destination, shave the head, and then the message would reveal itself. So steganography can be used with different medium. It has been used with text, with audio, even objects, but in practice the most popular medium will probably belong to that of digital images, and there is a good reason for that. Now consider what an image is, right? An image is basically a matrix of square pixels arranged in columns and rows. Now in a grayscale image, each of these square has an assigned intensity between 0 and 255. In a colored image, each of these square is an array of 3 values representing RGB, the red, green, and blue. So I'm gonna go to this website and I'm gonna show you. For example, if you really inspect on each of the pixel, you will see that there's 3 values: R, the G, the B. So R216, that's the red pixel, that's the red channel, green 108, and blue 80, and that gives it this perfect color at that perfect spot in that perfect location in that pixel. And if you scroll down, you could look at different values, you see that. And you imagine that something that has something that is very close to white would have a value very close to 255. So 255, 255, and 255, that would be a complete white. And a value that is close to black, for example here, would be somewhere would have values close to 0. So 0, 0, 0 would be complete black. So in this case, you see this is a complete 0 for the blue. All right. Then I want you to imagine this. For a value that looks like this, 252, 216, and 160, what it does is each of this value, 0 to 255, that's basically 1 byte. So a byte is basically 8 bits, right? 8 bits to a byte. And what happens is, if you take 252 and you represent them in bytes and bits, you actually see like 0 and 1, 0 and 1, 0 and 1. And what happens is that you could then arrange this and then take the last 2 or 3 digits or last 1 digit and change them and manipulate them in very, very small ways, and it would be nobody could tell. From a naked eye, you can't tell. So a good image that looks like that, right? From zoom out, you see that this is a perfectly good image. But if you really zoom in and zoom in and you zoom in and you zoom in, you will start to see that there are actually values, and you just have to manipulate those values. You don't manipulate them in the RGB form, you actually represent them in bits and bytes first, and then you change them. And so each of these pixels would actually just be RGB. For example, you know, the one I just mentioned, that the ones closest to white would have very high values, closer to 255, 255, 255. A perfect white would have been 255, 255, 255. If you can find a perfect white, for example, maybe at the top, if you find a perfect white maybe at the top, you see that it comes very close to that, 255, 255. And a perfect black let's find a perfect black, maybe somewhere around this area, or maybe somewhere around this area. So let's do around somewhere at the bottom, maybe around this area. You will see that it comes very close to 0, 0, 0, maybe none of them, but yeah, a perfect black, a full black would have been that. That means there's no red, there's no green, and there's no blue. All right, and what this allows you to do, and before you do this, right, you could do a quick math here. So if there's RGB and there's 256, 256, 256, meaning when I say 256, it means 256 bits, right? But 8 bits to a byte. So what does it mean? It means 8 bytes, right? So if you take 8 bytes, 8 bytes, 8 bytes, or you take 256 times 256 times 256, how many permutations are there? So 256 basically multiply by 256, multiply by 256. How many combinations of colors are there? The full spectrum of that, right? So essentially my question is a full true color image that has 24-bit color depth, 24 because 8 bits, 8 bits, 8 bits. How many colors are there on this one spectrum of a 24-bit color depth? So in total, if you take 256 multiply by 256 multiply by 256, you get close to 16.77 million colors in each of these square pixel. So what I'm saying here is that each of these small pixels that you see, or each one of them, like these small tiny pixels, how many combinations of them are there? How many total colors are there on the spectrum? 16.77 million, right? That's quite a lot. And realistically, the human eye cannot perceive the entire available palette. Humans see less than 16 million colors by far, you know, just easily, they're not even close. This makes it possible to sneak in some data and still preserve a virtually identical copy if we're clever about it. What I mean by being clever about it is to alter what is known as the least significant bits. So the image that we're using, we refer to that as our cover image. This is our cover image, and we want to hide some message in it, right? So by least significant bits, what I mean by that is the bit that is the rightmost to the string, right? So if you have a value like 10101111, then you want to take the last two. So let me open up my Python terminal and I'll show you what it means later. But it is referred to as such because it has the least effect on the value of the binary number. So for example, if I give you a number like 10101011, so this is a number, right? Now, what number can you change that has the least impact on the actual value of this number? So you would think that, okay, well, I would have to change the rightmost. It wouldn't be the leftmost, just like in decimal numbers. If I give you, let's say I give you $695,000, and $441.23, for example. Now, what value can you change here that has the least impact on the full amount? Well, you wouldn't go in and change 695 to 495. You wouldn't do that, but you would have been okay if I changed 23 to 21, for example, or 23 to 39, for example, or 39 to 114, for example, right? So the least significant bit of the number. Same thing in the binary digit system, right? So that's the least significant bits. So that's what we mean by being clever about that. Okay, so when you hear the word least significant bits, it also refers to the algorithm of the steganography method that we're going to be using, and it is referred to as such because it has the least effect on the value of the binary number, just in the same way as the rightmost digit in a decimal number, just like this example that I gave you, 695,441.15. What number can you change that has the least significant impact on the full number? Well, it would be the rightmost examples. So the less digit you use, the less perceptible any changes to the cover image would be. That makes sense. All right, if you use a lot of value, if you change the last 3 digits, now the changes would be a little bit more obvious, but generally speaking, if you use like two numbers, and I'll show you some images later, you won't be able to tell, right? In fact, I can actually show you some of the examples already. So this is one example, and this is another example, and I put them next to each other, side by side, and you tell me whether you can tell whether there's any differences. So this is the one with the embedded message. This is Bunaken. Bunaken is in Manado. It's where my wife is from. So you can't tell any kind of differences. They're exactly the same, right? And I'll give you another example. This is one with the message in here. So that earlier I used the Bunaken example. Now I use Ubuntu. Can you tell which one has been tampered with? Which one contains the image? You can't really tell because what I did was very subtle. It was just a message hidden within by altering just that small tiny value. And I'll show you the code and then we'll do some demos together. I probably won't write all the code for you like one by one, but I already did the exercise, so I can do this. And maybe in a future class, if I have 3 hours, 4 hours, I'll do that you know, in a live coding session, but not today. All right. So later on, as we do this code example, what we do is we just stick to 2 digits, and that's actually, I kind of have this open up already, so I set this up to be 2. I'm gonna have the code on my GitHub. You can change that to some other numbers and try and tinker around with that, and maybe have it to 3 and see what happens. All right. And then what we're gonna have is we're also gonna be using we're gonna just be using, actually the only real dependency here is CV2, math is built in, OS is built in, so CV2 and NumPy. But if you install CV2, NumPy come as part of it anyway. So really you don't, NumPy is really like it comes with CV2. So if you do a pip install CV2, CV2 comes from OpenCV, so you have to do a pip install OpenCV-Python. So that's gonna be something like this. So it's gonna be like pip install OpenCV-Python, and you just run that. I already have that, so it's not giving me anything. All right, and then you say import CV2, import NumPy as np, and then you do need to learn a couple of things here if you've never seen those before. Now, the first thing I would say, like some of you may look at it and like, oh, I'm not familiar with the left shift and the right shift. Now, what is that? What are these bitwise operators doing? What is this two funny angle doing? So this is basically shifting. This is called the bitwise operators, right? They're basically shifting it by left shift it or by right shift it. So let me show you. Let me open up a Python shell and I can run some examples and show you what I mean by that. All right. So if I take 1. This is 1, but how do I represent them in binary? Well, in Python, you can just do bin. Let me actually zoom in a bit, like this, right? Bin1. Bin1 basically says, what is a binary representation of 1? Now that's just gonna be 1. But what about 2? That's just gonna be 1, 0. What about 3? I think if I stop here, I think you can guess what 3 is. 3 basically adds, it increment that 0 to be 1, so it will be 1, 1. So let's see that, 1, 1. What about 4? Now it just moved and it goes to 1 because this is a binary system, right? So 1 will become 0, 1 becomes 0. Now it moves 1 more, it adds 1, and so now it's 1, 0, 0. So if I go to 5, now it will be 1, 1, 1. What I want to show you about this left shift and the right shift, the bitwise shifting operators, are basically this. If I do a left shift, what happens is that it places new bits on the right hand side, then they're all going to be 0. So that has the effect of taking 2 to the power of y. So let me show you what I mean. If I said this is 5, let me say 5, right? Okay, 5. And if I say take this and I say move this by 2, let's see what we get, right? So what we get is that we basically have the number 101, but then it adds 2 0. What about 3? What is that? Well, now you get adds 3 zeros after that. So it's very, very simple. It's a very simple idea. It adds 4 after that. So what would that be? So let me show you. 5 would still be 5, but what if 5 to shifting 2, you give us 20, and that has the same effect as taking 5 and then what, and then say multiply by 2 to the power of 2. We need to put down everything in a bracket, so you're not using the caret, you're using the double asterisk. So depending on what languages you're doing these exercises, if you use this in R, you probably use the caret. If you use this in JavaScript, you do. So depending on what languages, okay? But you have to do something like this. But that would give you the effect of that. So let's take a look at 3. Now, if you say 2 to the power of 3, what are you gonna get? 2 to the power of 3 is 8. 8 times 5, that's 40, right? Then, so on and so forth. And that would be the same. This would be the same. The 3 would be the same as this value. So if you take bin 40, then you get this, right? So that's what a left shift operator and right shift operator is doing. And I hope that you can play around with this example, try to intuit about it. But what we're doing here is that we're going to use some of the left shift and right shift. Again, I'm not going to walk you through all single piece of line of code, but I'm going to just show you, generally you can do this in like, 60 lines of code. Really simple, the encoding part of it. And then encoding is basically, this is also in cryptography, we actually call this insertion. All right, we call this insertion, meaning we try to insert a message, a secret message into the image itself, and then you can just print successfully embedded. I want to show you also that this is a two-way process. You can also decode that later. So I have the decode open up on the left, so that's there. Let me move this over to my right of my screen so you can see all of that. Another small details is we're gonna use, no matter what the image is, no matter what the input image is, you see that I have JPEG. But what we're gonna do is that we're gonna say, okay, I am cv2.imread. If you follow any of my computer vision courses or any of my videos on YouTube, you will see me using this. So this is nothing new to you. I am stands for image, read the image, read any color, and then print a shape, and then try to take the shape, try to find out how many bytes can we use, right? So we take the height and then multiply by the width. So remember when we read that in as a NumPy, using OpenCV, the first one is going to be the height, then the width. So multiply that and see how many bytes can we use, and then we basically change the message a bit. We try to use a simple marker to tell us where this is the number of what is the length of the message. Then we put a simple marker, and then that is the actual message, so that when we decode, we can also verify that, okay, that's the length of the message, it matches. We can do something like that. And if it's greater than that, if the length is greater than that, we then show that, okay, the message is greater than capacity. Now capacity is another word that you come across. Capacity basically says how long can the message encode. Obviously, if you change this number, the 2, you will change the capacity. So lower end makes the picture less loss, so the picture is gonna still look very sharp, just like the actual image, with very little differences. But of course, it's going to give you less storage, because you only, out of the whole byte, you're only manipulating the last 2 digits. So it's instead of so you have let's say the number is 254, right? Let's say the number is 254. So remember I told you that the maximum byte is 255. If you take that number, this is how it looks like. Now you're only manipulating the last 2 digits here. So the 1 you're going to change that. So obviously you're going to have less storage. If you change this to 3, you have more storage, right? More capacity. So that is also something we check for. And then one detail is that we're going to use the PNG, right? Why do we use the PNG? Well, compared to the JPEG, why is PNG better for this kind of scenario? Well, PNG format is a lossless compression file format. So it's perfect for this. It's perfect for restoring message correctly. JPEG format, the JPG or JPG format, that's a lossy compressed file format. So the biggest advantage of using PNG over JPEG is that the compression is lossless, meaning there is no loss in quality each time it's open and saved, meaning the image quality will be the same roughly before and after compression. But the trade-off with PNG is that the lossless compression generally creates bigger files than the JPEG counterparts, since they retain much more information. Okay, and I want to show you, like, when we do the encoding, and this is the encoding, and then the decoding, basically we just do the inverse of that. So this is a two-way process. So maybe I could, if I'm a criminal, for example, and I have a stash of things that I shouldn't be selling, black market, I have a black market location, I have some stash, or maybe I have some bad websites I have about, let's say, adults websites that I don't want anyone to know, and I encode them, and I want to send it to my buyer. So I'm the seller, right? I'm the black market seller. I want to sell it to my buyer. So I could actually create an image and then use what you learned here, the steganography, and embed the image, and I could send it over to him. I don't have to worry about anyone intercepting, because the image would just look completely natural, original. But that person can then decode that and get the message out. And I'm going to show you the process later when we run the code here. All right. But what happened is that in this encoding, you see that generally it's the opposite of that. So for example, here is the ORD. And what does that do? That basically returns the Unicode code from a given character. So for example, my name is Samuel. If I take the first character and I said art of S, whoops, forgot to put that. So that's 115, right? So you see that when I want to inverse 115 back to S, what do? See, in here, I say CHR, that's the character of that. So let me go and say character 115, and I get S back, right? So this is the inverse of that. So when I first do this, I take the Unicode, and then I go through the shift. Now in here, instead of doing the right shift, I'm going to do the left shift, which is the opposite. And then instead of doing the Unicode first, I'll do the Unicode last. So basically it's a complete reverse of the encoding process. So encoding process, I'll basically take that, change that to a number. Why do I need it to be number? Because S itself, I can't really encode that. I need S to be in a number, so I can take the number, make them into binary, and then I can now plug them into my pixels, correct? And then I will have to do the opposite of that, right? Take the numbers, bring them back into characters, and then display them. So I'm doing the opposite. So this is a step 1, step 2. Here it becomes step 2, step 1, just to do the opposite of that. And that's kind of it, actually. All of that is kind of everything else you could sort of read on your own. You kind of just need to learn a little bit of if you're very new to the shifting operations and stuff, that's what you need to learn. But generally that's kind of it. Now I can do an encoding. So how do I call the script? I say here, so here's the image. If I can pass in an image path, I can pass in a message. So I could do something like Python, and I can do something like encode.py, and then I could pass in a second argument, which is my image path, which is like that, and I can pass in some bad website that I shouldn't be promoting, but I wanted to communicate that, and I want to embed that, for example, right? So let me do that, and I said hit enter, and now it says successfully embedded. I want to remove all the print statement, obviously. I don't want a lang message, I don't want all of this, but anyway, that's yeah, remove all the print statement. So now I have this embedded image, and I could look at the embedded image, and that's what you see earlier, and it has nothing. It just completely look very genuine, and you won't really tell the difference, right? Anyway, now I could go and decode that message. So in the decode message, all I need to do is to say Python, and I can say decode.py. Remember that the secret message is what I want to come out. So I want to extract and I want to print the message. Now it just look at the image path. I can pass in an image path like this. I said, okay, this is the embedded image. Now the buyer who received my image could now decode that and find out the true true message. So let me do that right now, and I get the badwebsite.com, and that's kind of the whole encoding and decoding, right? Now I want to say that the use of steganography in the wrong hands is an extremely dangerous tool. Some call it the undetectable cybersecurity threat. Some say that this cyber threat is perhaps among the most stealthiest. And you can read about the history 2,500 years ago. The Spartan king Demaratus. This is a different story. He learned that Xerxes the Great was planning to invade his homeland. Publicly opposing him wasn't an option, so he took a different route. He sent 2 wax-colored slates, so on and so forth. If you go back to the original message, the original article, it says the point of this, right? The point of standard encryption is to hide the content of the message. But even if you're detected sending a message no one can read, you will still be suspected by the authorities for sending a coded message, right? So if you're trying to do encryption and decryption, everyone knows that you have something to hide. They just, if your encryption algorithm is good enough, they don't know what you're trying to say, but they know you have something to hide. With steganography, you try to hide the fact that communication is going on at all. You're just sending an image. You're putting an image on Reddit. You're putting an image on your forum, on your website, on whatever, 4chan, whatever website, right? And no one knows that you're making any kind of communication. And so that is what makes it so stealthy, I think. And so one may imagine that a bad actor or a group of bad actors can use steganography to conceal, let's say, links to sites that are harmful and dangerous. Think about illegal adult sites that exploit a certain demography. Think about extremist groups that are commonly affiliated with terrorism or any kind of hate groups, or just any kind of content that would otherwise be censored by the mainstream internet. Anyone in a circle would upload their stash, promote the links to that stash on the dark web. But now they can do it publicly and openly. They can do it on anywhere on social media using digital images that look legitimate and authentic looking. And some take this even a step further, performing what is known as a steganographic attack. Now for these attackers, hiding malicious code in an image or audio file is only half of the battle, right? They also need a malicious or buggy program on your target's computer, to run that code. So that's why criminals who use steganography to deliver bad software into systems they already know that the host has already been compromised anyway, right? I'll give you an example here. So I think there is the cyber thief, right? So here. So a cyber thief might try to deliver a PNG filled with bad code to a browser with a known vulnerability in how it loads PNG. So it knows that you're using a browser that has a vulnerability, it's a known vulnerability, and it knows that it has a vulnerability with PNG. So it would then load this in there. Now the PNG looks just like your normal PNG. You don't suspect anything at all, except it's manipulated in that small way, and then a hacker might just break into a corporation's network and then use malicious PNG to sneak past security features and deliver even more malware. So in short, they could use this, they could do this, and it requires 2 steps, and that's why steganography is often reserved for targeted attacks instead of blanket ones. Okay, so these are all you can read them up, you can study more about that. But I just wanted to show you this thing and discuss about steganography. I don't know if I would have time to put together a video that is like 3 or 4 hours where I go into the code and explain how to do the shift. It's actually relatively straightforward, very easily understood. It's not the only method of steganography. There are other ways of there are other ways to sort of perform this kind of steganography. But this method here, the least significant bits, I think that's sort of the introduction to this, and it's quite robust. It's not really the most robust, but it has good storage. It's well understood by people, so that's why I picked that to start with. So that's steganography in under 15 minutes. I hope you learned something new. I make videos on programming, mathematics, blockchain engineering, and other things related to computer science that I find fascinating. Now if you make it this far, please consider subscribing, share the video to a friend. I hope to see you soon. Bye.